national sprint problems. And then once we complete these, we will move on to target and then team. So let's just go ahead and get started with number 23, a three-digit number is selected at random from all three-digit numbers 100 through 999. What is the probability expressed as a fraction that the number selected is a perfect square? So we're selecting an integer from not 100 through 999 inclusive, and we want to find the probability that it's a perfect square. So our probability is going to be the number of cases that satisfy our restriction and the total number of cases, right? So our total number of cases is just going to be the total number of numbers that we can select here, right? And if we have this range inclusive, the total number of numbers that you can select is just going to be 999 minus 100 plus 1. So why do we have this plus 1 right here? Well, I mean, you can think of it like, what if we had the range 1 through 2, right? How many possibilities are in here? Well, you could select 1 or 2, right? So that's 2 possibilities. So it's not just 2 minus 1, but you have to add a 1 to it. So this is going to be the total number of possibilities we could select. So that's just going to be 900. So we know our probability denominator has to have 900, and we now just need to find the total number of possibilities that satisfy our case, which is going to be the total number of perfect squares that are three-digit numbers. So now we're not going to list out all of the perfect squares, right? That would take way too long. What we should do is find the lowest perfect square that is a three-digit number and find the largest perfect square that is a three-digit number, and then all the perfect squares that are in between them are going to satisfy our conditions, right? So then we just find that range. So the lowest three-digit number square that we have is 100, right? That's just 10 squared. And then the highest, it's a little bit harder, but I mean, you can first estimate it, right? So like 30 squared is going to be 900, but that's too low. Maybe try 31 squared. So that would just be 31 times 31. You multiply it out and you get 961. And then you see that if you do 32 squared, it's going to get too big, right? So our largest perfect square that is a three-digit number that we can get, oh, whoops, not 30, it's going to be 31 squared. It's going to be 31 squared or 961. So again, all of the perfect squares that are in between these perfect squares are also going to satisfy our condition. So how many perfect squares do we have here? Well, we're just going to find the range of this, which is going to be 31 minus 10 plus 1, which is just 22. So now we're going to put this in our numerator and we just simplify. So that's just going to be 11 over 450. If you guys have any questions, just ask it in the chat and we'll try to answer it. Number 24, solve for x. We have 3 to the x squared over 3 to the 3x equals 19. And okay, so first let me explain this thing. So if you have like a to b to c, people might get confused on like, what do you do first? Do you do b to the c and then a to b to the c, or do you do a to the b and then a to the b to the c? So the convention is whenever you have this, you always want to do the higher exponents first. So in this case, it's like you have parentheses around these, you do b to the c first, and then you do a. Okay, so we have 3 to the power of x squared in our numerator and 3 to the power of 3x in our denominator. So what we can do is we can simplify this to 3 to the x squared minus 3x. So why can we do that? Well, it's like if you have some base a to, let's say, power of x, and it's over the base a to some power of y, then this is going to equal a to the power of x minus y. It's also like if you have a to the x times a to the y, then this is going to equal a to the x plus y. And so this makes sense, right? Because you can rewrite this this a to the y in the denominator as a to the negative y, the negative signifying that it goes in the denominator. And then if you use our property here, then you still get a to the x minus y, which is what we had before. Okay, so we can apply that here. We have the base of 3 going to some power, and so and because we have it in the numerator and the denominator, we can just subtract these exponents and have our base 3 to this exponent here minus this exponent here, and this is going to equal 1/9. Now, what we can do here is we can put 1/9 as 3 to the power of something, right? Because 9 is just 3 squared, right? And if you have 3 squared in the denominator, that's just going to be 3 to the negative 2, right? And putting our 1/9 as 3 to the power of something is really good here, right? Because we have 3 to the power of something on the other side, right? So if you have 3 to the power of something on this side and 3 to the power of something on this side, then the thing that they are to the powers to have to be equal, right? So then we can just we can simplify this a lot, and we just get x squared minus 3x equals -2. And now we just have a quadratic equation that we need to solve, right? So I hope everyone knows how to do this. And we can just factor this here. So that would just be x minus 2 times x minus 1 equals 0. So that means x will equal 1, 2. All right, anything you want to add, Bill?
No.
Okay. Let's move on. If p is the least common multiple and q is the greatest common factor of 36 and 54, find p minus q over 10. Okay, so we should just find the least common multiple and the greatest common factor of those two numbers, and then we do some arithmetic with them. So we have 36 and 54. Let's just do GCF first. Okay, yeah, let's just do GCF first. It doesn't really matter which one we do first. So what we should do here is we should prime factorize these numbers. Why? Because doing greatest common factor and least common multiple is a lot easier when you have their prime factorizations. So 36 prime factorized is just going to be 2 squared, 3 squared, right? Because 36 is just 6 squared and 6 is just 2 and 3. And then 54, well, that's 6 times 9, so that's going to be 2 times 3 times 3 squared, so that's just 2 times 3 cubed. So our greatest common factor is we're going to take the smallest, like we're going to look at each of the primes that we have here, and we're going to take the smallest power that any one of these have, right? So like we're going to first look at our power of 2. So our lowest power of 2 is just 2 right here, so our GCF is going to have 2. And then our highest power, we're going to look at 3 now, and our lowest power of 3 is 3 squared. So that means our GCF must be 2 times 3 squared, and that's just going to be 18. And our least common multiple, we can do something slightly different, and that's to look at each prime, but you take the highest power of each one. So least common multiple, okay, so we're going to start with 2, right? And our highest power of 2 is 2 squared, and our highest power of 3 is 3 cubed. So this is going to be our least common multiple. And this is just 4 times 27, so that's just going to be 108. Okay, so now we have our least common multiple and greatest common factor. We want to do our least common multiple minus our greatest common factor over 10. So that's just going to be 90 over 10, which is 9. Anything you want to add, Bill?
Yeah. No, not really.
Yeah. Yeah. Okay, simplify and give your answer as a mixed number. We have this very large fraction tower. So we want to do the fraction at the very bottom first, and we want to work our way up. So the thing, I'm not sure why they have the plus ones, right? I mean, we can just go ahead and simplify all the plus ones, right? So 1 plus 1 is 2, and then 2 plus 1 is 3, and then that's 4, and then that's 5, and then that's 6 over 6, right? and we want to start with our very bottom thing here first, right? 6/6 is just going to be 1. And then 5/1, that's just going to be 5. And then 4/5, well, that's just 4/5. And we have 3/4/5, and then 2 over that, and then 1 over that. Okay, so if we have 3/4/5, so we're just looking at this for now. We can bring our fraction to the top if we take its reciprocal, right? So that would just be 3 times 5/4. And we still have the 1/2 stuff. And then, so what is this going to equal? Well, that's just 15/4. And we still have the 1/2 stuff. And we can do the same thing with this. So bring our fraction to the top and we have to flip it. So then we have 2 times 4/15. So that's just 8/15. And then, if you have 1/fraction, that's just its reciprocal, right? It's like you can bring it to the top, but you just have times 1, so that doesn't do anything. So it's just its flip thing. So it's just 15/8. Now don't forget that it wants the answer as a mixed number. So see how many 8s can go into 15, which is just 1, and you have a remainder of 7. So it's 1 and 7/8. Anything you want to add, Bill?
So yeah, in this case, just know that if you're working with like a fraction and a fraction, you always want to use like the outermost, I guess, fraction first before doing the bigger fraction.
Yeah. I mean, yeah, you can also tell with the the size of the fraction thing. So you want to start with the smallest size of the fraction thing. All right. Oh, whoops. Number 27, given rectangle QRST with Q at that point and R at that point, if diagonal QS has a length of 2 times root 65, find the area of the rectangle. All right, so we should start with graphing the points because it always helps to visualize stuff so we can see what's happening. So let's just do 1, 2, 3, 4 like that. All right, and then we have Q at -2, 4. That's going to be right here. And we have R at 2, -4, so that's going to be right here. And it says if the diagonal QS has a length of 2 times root 65, find the area of the rectangle. All right, so whenever you have a rectangle, whoops, my rectangle is so bad. Okay, if you have a rectangle, let's say it has points A, B, C, D. And these are just our points, okay? There are 2 weights, or okay, so like, so yeah, there are like 2 weights to denote this rectangle, okay? So you can say, like, if we're starting with A, we can say A, B, C, D. We're going around the points like this. We can also say A, D, C, B. That's also valid. But you can't say A, C, and then the other stuff. So you always have to go, your points, you always have to go like clockwise or counterclockwise. You can't skip to a point that's not connected to this point. I hope that makes sense. So if we have a Q, it says we have rectangle QRST, right? So that means QR, our line QR, this has to be a side of the rectangle, not a diagonal, because we have 2 adjacent points here, right? Whenever you have 2 adjacent points, they always have to be connected by an actual side. So this has to be a side of the rectangle. And then the diagonal QS is going to have a length of 2 times root 65. So there are two ways our rectangle could go here, right? It could go in this direction, or it can go in the other direction. It doesn't really matter which direction we're working with here, because like, it just wants the area, and there's nothing specifying which direction we have to go, right? So So let's just like without loss of generality, let's say that the rectangle goes to this side, okay? And then so then we're gonna have a rectangle something like this, maybe. Okay, and then following our naming technique, S must be here and T must be here, right? So that we have QRST. And this makes sense, right? Because it says the diagonal QS. Oops. Okay, whatever. Okay, and this makes sense, right? Because it says the diagonal QS has a length of 2 root 65, and in our depiction, QS is a diagonal. Now, there are probably multiple ways you can do this. The easiest way I see, maybe, is to find the length of this line segment. We can do that because we have the points of Q and R. And then we can just use that and use this to find the area of this triangle, which you just double to find the area of the rectangle. So, I mean, so okay, so we can draw another triangle like this. So this is at Q is at -2, 4, and R is at what, 2, -4. So this side length of the triangle is going to be 4, right? Because this goes -2 that way, and this goes 2 that way. My drawing isn't perfect, but yeah. And this side length is going to be 8, right? Because um, this is at 4, and this is at -4. Now we can find the length of this segment by using the Pythagorean theorem, right? That's just going to be 16 plus 64 square rooted. So that's just 80 square rooted. And let's just keep it at square root of 80. I'm not going to simplify it. So now we can look at this triangle right here. So there's going to be a right angle here, right? Because of like this rectangle. So that means we can use the Pythagorean theorem on this triangle with this side and this side to find the length of this side, right? So let's just call this side x. So then we have 80 squared plus x squared, and then that's going to equal 2 root 65 squared. So we can find x squared. That's just going to be 2 times root 65. So that's 65 times 4, right? So that's just 260, and minus root 80 squared, that's 80. So x squared is going to equal 180. Yep, and x is then going to equal square root of 180. So now we know x equals square root of 180. So we can find the area of this triangle with this side and this side, right? Because those are the legs of the triangle. So we can say that the area of that triangle is going to be 1/2 times root 80 times root 180. And the rectangle is just two of those triangles, right? So the area of the rectangle is going to be 2 times the area of this triangle. And so the 2 and 1/2 cancel out. So then the area of our rectangle is just 80, root 80 times root 180. So that's just root 80 times 180. Okay, and then how do we do this? Well, I think we should just like kind of prime factorize it here. So we can take out a 10 from both of them, right? So then we have 10 squared. And then we have 8 times 18. So 8 is 2 cubed, and 18 is 2 times 9. So, and 9 is just 3 squared, right? So we can take a 10 out of the square root. We have 2 to the 4th, so we can take 2 squared out of the square root. And we have 3 squared, so we could take a 3 out of the square root. So that's just 12 times 10, so 120 square units. And that's our answer. Anything you want to say, though?
So for this problem, if you notice during the process, you don't necessarily have to draw the whole graph. This problem, you can do it completely without drawing the graph. If you can just like visualize the problem, the graph is not necessary. So if you're if you're good enough with it, you don't have to spend time drawing the graph, and you can just do the algebra.
Yeah. Like, I mean, if you already realize that Q and R is going to be one side of your rectangle, and Q and S is going to be like the diagonal of your rectangle, and then you can just you can just find this side length with those points, and you don't have to draw it out. That would be faster. And then you just like do the same thing. And anything else you want to say? Do you think this is like the best way to do it?
Okay. Let's see. There's probably a better way to do this. I feel like. Um, but I mean, this is probably the most straightforward way to do this, but there might be a easier way to just find it. But this is definitely the most straightforward. And
Wait,
for your,
what would you be thinking then?
I mean, if I was given more time, so on a test like this, normally your best plan is just to go with the first thing you can think of and not waste that much time thinking, trying to think of a solution. If you can think of a solution that works, you should probably just stick with it. But if I was given more time, I would probably try to find like the exact the exact coordinate of S, probably, because I feel like that is calculatable. You can find it.
Um,
But that also involves
I
like,
I think that would be worse. I think that would take
yeah, that
more
would be
time.
worse. I'm just saying that's a different way to do it because that does involve like a more like
Yeah,
complicated
yeah.
stuff.
I mean, like you'd have to like find the slope of this, and then um, like you can't just use it with the line of the length of this, right? You have to
Yeah,
have the slope of this, and that's kind of bad. So
yeah. So yeah, I mean, this is a fine method. I mean, this did take a while, but I mean, once in a while you will encounter a problem that takes a while. So this is fine, I think.
yeah, okay. Let's just move on. Okay. Um, we have number 28. A father gave all of his money to his three daughters. To the first, he gave half the money plus $1/2. To the second, he gave half of what was left plus $1/2. To the third, he gave half of what was left plus $1/2. The second daughter wants to purchase a $6.25 Mathcounts t-shirt. How much more money in dollars does she need? Um, so a father has some amount of money at the beginning. Let's just call that X. And then he gives some to the first daughter, and then he gives some to the second daughter, and then he gives some to the third daughter. Um, but I mean, do we assume that he gave all of his? Oh, it says he gave all of his money. Oh, okay, okay. So so okay, so okay, so the first daughter is going to receive half of the starting money, right? Plus $1/2, so plus like 50 cents, right? After that, I'm interpreting that right?
Um, yeah,
Like he gives half the money and then he
yeah,
gives half a
yeah,
dollar.
yes.
Okay, yeah. So he's going to give this much, right? That's what it says. So if he's going to give this much, the amount he has left after he gives this to the first daughter is going to be his initial amount x minus this amount, right? So that's just going to be 1/2 x minus 0.5, so $0.50. And then to his next daughter, he gives half of what he has right now, which is that, and then he gives another $0.50. Okay, and then so what he's going to have left after this is going to be what he has right now minus the stuff that he gave, which is this stuff, right? And then plus $0.50. Now this is the same as that, right? And this is like 1/2, so that's just going to be, we're just going to be left with 1/2 of that, but plus another 0.5 at the end. Oh, not plus, it's going to be minus, right? Yep. So we're going to have a minus at the end because this minus goes to this 0.5, right? So this is the amount he has left after he gives money to his second daughter, and this is the amount of money that his second daughter got. Let's call this 1. Let's call this 2, and okay. And then to his last daughter, he gives a half of what he has left, which is what we have there, and another 0.5. So this is what he gave, right? So if he gave this much, the amount he has left is going to be what he had, which was that, minus this. All right. Minus this because this is what he gave to his last daughter. Yep. And then we can see that this thing right here is the same as this thing right here, right? So, and this thing is being multiplied by 1/2, right? So we're minusing this thing, like we could call it y, and we're minusing 1/2 of y here. We're going to be left with 1/2 y at the end, right? So we're going to have 1/2 of all of that. And don't forget this 0.5, that was not in the y, right? So that's going to be a minus 0.5. All right, this is the amount of money he has left after he gives his third daughter money, right? And then it says that he gave all of his money away, right? So this must equal 0. So now we have to solve for this, and we're going to solve for x, right? Like if we solve for x, then we can plug in x to this, and then we can solve for the amount of money that his second daughter got. Or actually, we could just solve for we could just solve for this. We could just solve for 1/2 of 1/2 x minus 0.5. Like if we call that y, we can substitute y into here, right? Because this is all we want. So we substitute y into here, then we add $0.5 to it. So that would save us a little bit of time. So let's just do that. So if we call that y, then we just have this. So move 0.5 to the other side and multiply by 2 on both sides. So then we're going to have 1 on this side, right? And then we add 0.5 to both sides. So we get y equals 1.5. So then the amount of money that his second daughter got is going to be $1.5 plus $0.5 is $2, right? All right, so she only got $2, but she wants a $6.25, or she wants a $6.25 Mathcounts t-shirt, shameless promotion. How much more money does she need? Well, that's just going to be $4.25, which is her answer. Anything you want to say, Bill? This is kind of a
this was kind of a long process.
Yeah.
So in this case, if you want to look at the problem, let me show it. So if the father ends with zero, right? If he ends with 0, then so each time he's giving 1/2 of it, 1/2 the original.
So right now Bill is working on his screen. So to view his screen, join the second Meet link that we post. Yep.
So yeah, well, it'll be 1/2x minus 0.5. So before he gave her the, so this is for the third daughter. Before he gave her the 5, the guy had 0.5, right? And then before, how to put it, the guy had 0.5. And so this was 0.5 is how much the person had after he gave the third daughter half of his money. So 0.5 is half of his money. So before that he had 1. And so before he gave the what the so after he got done with the first 2 daughters, he had $1 left. And so if we keep working backwards, or before he before he gave the second daughter her half dollar, he had 1.5 left. And before he gave half his money, he had $3. So we know that when he first got to the second daughter, he had $3 left. And so from here, we know that he gave half of his money to the second daughter. So that's 1 point. Is for the third daughter? For second? So we know that he had 1.5. He gave the daughter 1.5 and then he gave her another 0.5. So we can see from this, just this, that he gave her $2. And then from there we can work out that she needs 4.25 more. Does that make sense? Okay.
Can you hear me?
Yes.
Okay, my microphone wasn't turning on for some reason. But yeah, you can't just work backwards like that, right? Like, yeah, like basically what Bill said, and that would be significantly faster. So yeah, I guess just looking at like a kind of long thing like this, maybe realize that like you don't have to use like algebra, you could just work backwards. So yeah. Okay. Anything else you want to say?
Um, just that, when you're facing something like this, like Austin here, he did the entire thing. You really don't have to do that. You can just think a bit. Like my method was I kind of just like bashed it and didn't really do like algebraic or anything, and that's totally fine a lot of the times. A lot of the times, just bashing it and not really doing it concisely, that's probably the fastest method to do something.
Yeah. Okay. Let's go into number 29 here. What is the maximum number of distinct lines that can be drawn through 10 distinct points if no three of the points are collinear? All right. So what this is saying is that we're gonna have 10 distinct points. I don't know. Okay, let's just say we have some points, but none of the points are collinear. So what does collinear mean? Well, it means like you have 3 or more points that are all on the same line. Okay, so it's saying that no 3 of these points are going to be in the same line, right? So yeah. Okay, and then it wants you to find the maximum number of distinct lines that can be drawn through them. All right. So so this okay. So should I like okay, I'm just going to work through it conceptually for now. Okay. So let's just think of one point, okay? Okay, sure. Let me draw a drawing. I don't even care. So it's like so one way you can view the points as, like one way you can put the points as is a like a regular decagon, right? Um I don't know. Can I draw that actually? Oh, very cool. Yes, okay. Here is a regular decagon. Um you can view the points as being on a regular decagon, right? Because there are 10 points in a regular decagon, and none of the points are going to be collinear, right? That's pretty obvious, and like that, regular polygons are like that. And my brush size just randomly changed. All right. So again, it's like we can view the points as being on the vertices of this regular decagon. And we want to find the number of distinct lines that we could draw. So like we could draw this line, right? And then we could draw this line, and then this line, and so on like that. And then we can draw from this point, we can draw this line, and then so on, right? And we want to find the number of lines that we could do that. So let's just focus on this point, okay? If we focus on this point, we can draw 9 lines, right? Because there are 10 points in total. And if we focus on this point, there are 9 other points that it can connect with, right? And so we could just do this to all of our points, right? Every other point is going to have 9 other points to connect to as well, right? So you could think of it as we have 10 points in total, so that's 10, and then it can connect to 9 other points. All the 10 points can connect to 9 other points. So it seems like you'd have 10 times 9 lines, right? Well, you have to be careful. Whenever you do this, you're actually repeating every line twice. Why? It's because, like, for each point, for each line, you're counting it twice, right? Because you're counting it once for every point that it's connected to, right? Like, if we just look at this line, we're going to count it once when we're looking at this point, and we're going to count it another time when we're looking at this point, right? And like same for all the other lines, right? There's nothing special about this line. But so that's not really an issue though, right? So we can just because we know that this thing has counted all the lines twice exactly, we could just divide it by 2 to get the actual number of lines. So then if we divide this by 2, that's just 5 times 9, that's just 45, right? I hope that makes sense. Anything you want to say, Bill?
Okay, so yeah, that is one way to do it. I guess another way you can do it is that wait, often another way you can do it is just working like upwards, I guess. Just like because if you have say 2 points, they can make one line, and then if you add another point, both of those points have to connect to this line. So two is one, and then every time you those 2 points for 3 points you have to add two, for 4 points you have to add three, and so on and so forth. And that's another way to do it, I guess. And so if you have 10, it'll be 1 plus 2 plus 3 plus 4 all the way plus 9. Dot dot dot. One plus
Yeah.
2 plus 3
And
4.
and those are just the triangular numbers, right?
Yeah,
The
and then
triangular numbers are just like you start with 1, and you're gonna add plus 1 to it, and then you're gonna add plus 2 to it, and so on. And that's what we have here. So then you could just find like the 10th triangular number. All right. Anything else you want to say?
no.
Well, actually, not the 10th triangular number. It would be the 9th, right?
Yeah, it will be the 9
Because
because we're starting
yeah,
on 2 points.
yeah, we're
So
starting on 2 points.
yes.
Okay. All right. Let's just move on to our last question. find the sum of the values of x that satisfy the given equation. And we're given something here. Let me just write it down first. Okay, and the plus 6 is out of the radical, and we have equals 6. Okay, so we want to try to simplify it a bit, right? So we could subtract 6 from both sides, right? And that would give us this equals 0, right? And then this 6, we could just divide by 6 on both sides, right? So then we just have and 0 divided by 6 is just 0, right? So then we just have this. All right, so if we have the radical of something equals 0, when does the radical of something equals 0? The radical of something equals 0 only when the stuff in the radical equals 0 itself, right? And you could visualize that on the square root graph, right? If you graph square root x, it looks like this, right? And the only point where y equals 0 is at the point x equals 0. So if you have square root of x equals 0, that means x has to equal 0. All right? So basically, we just got, we just have this equals 0. And you can also think of it algebraically as you can square both sides. And because we have a radical and we're squaring both sides, we don't have to think of, we don't have to account for missed positive and negative cases, right? We went over that in our last meeting, I think. And that's if you square radicals, you don't have to worry about anything. But if you square root squares, then you have to worry about negative positive cases. All right, so then we just have this, right? And what does this equal 0? Well, this just equals 0 whenever any of these components equals 0, right? If any of these components equals 0, then it's going to multiply by the whole thing, and that's going to equal 0. And when do those components equal 0? Well, just when x equals 1, 2, or 3. All right. Anything you want to say, Bo? And this is just our solution.
Yeah.
Oh, okay. And so it says you want to find the sum of the values of possible x, right? So that's just 6. So that's our answer.
Yeah, this problem is fairly straightforward. Just you have to know that you have to know how square roots work, basically. Yeah.
Yeah, that was a fairly easy number 30. All right. Okay. So yeah, that was all of our 1990 national sprint problems, and now we're going to move on to target. All right, so AIME has fewer. Oh, wait, let me find a space. Oops. I'll use this space. AIME has fewer than 100 computer disks. When she stacks them by 11s, 10 are left over. When she stacks them by 10s, 7 are left over. And 3 are left over when she stacks them by 6s. How many disks does she have? Okay, the stacking stuff, it's like, so like you have some number of stuff, right? And then I don't know. Okay, so let's just say dots are a computer disk. Okay, you have some number of dots, and you're stacking the dots, right? Like in groups of 6, and then you have, you stack them, and you have some remaining leftover, some dots remaining leftover, and that's talking about the leftover stuff. So this is just the same thing as modulus, right? It's like you're dividing something, but you're looking at the remainder, right? So if we call the number of computer disks that AIME has as x, then it's giving us 3 modulus equations. It's giving us x modulus 11 equals 10, x modulus 10 equals 7, and x modulus 6 is 3. And it also tells us that it has to be fewer, x has to be fewer than 100. So honestly, I think the fastest way to solve this would just be to test basically test cases. And if you have multiple modulus equations in your testing cases, what you want to do is you want to test first with the largest modulus number equation first. So like we're just looking at the x's that satisfy that. That would be 10 and then 10 plus 11, which is 21, and then that plus 11, which is 32. And you can just list these out, right? And we're only going up to 100. So there we go. And then we just need to look from these possibilities, which ones satisfy these. So if the modulus 10 equals 7, that means its units digit has to be 7, right? And that's the only one we have here, so it's got to be this anyway. The modulus 6 thing doesn't even matter. But if we modulus 6 to this, so you can see that it works, right? Because 84 is going to be a multiple of 6, and this 3 larger than this multiple of 6. The right answer has to be 87. Anything you want to say, Bill? Okay, looks like Bill hasn't left for a moment, but this should be just pretty straightforward. Like if you have modulus equations with x like being not that big, so there are not that many tests to cases to test, then like testing cases is a pretty fast way to solve it. And you could kind of solve it faster if you noticed this equation as you were listing these out, right? So this is saying that the unit digit has to be 7, right? And our 11 stuff here, the units digit is always 1 less than the tens digit. So like if you knew that the units digit had to be 7, then the tens digit from this has to be 8. So then you can just get any 7. But yeah, let's just move on. Find the value of m expressed as an improper fraction so that this relation is not a function. Okay, so we have some x values as we have x values as negative 2m plus 1, comma negative 4. We have y values as negative 6m plus 8, comma 0. So when something is not a function, when you have an x value corresponding to multiple y values. So let's say like if you had a I don't know, if you had a mapping and this is your x and this is your y, something would not be a function if an x goes to multiple values of y. So like 1 goes to 2 and it goes to 3. So like you can also see that from like the vertical line test, right? Like if you have a circle, this is not a function, right? Because if you do the vertical line test, it crosses more than one point. And this is just saying like there are multiple y values for one given x value, right? So hello.
Hi. Hi. Yeah.
Okay. Am I being dumb on this one?
I'm finding out.
Oh, okay, I get it.
Okay,
I'm dumb.
so okay.
So it's not like those are my x values and those are my y values. It's okay, so it's like let's say you had the function x squared. Okay, you can say a point is 1 comma. Oh, okay, I'm so bad. Okay, you can say a point is 1 comma 1, right? Because 1 squared is 1. And then you can say another point is 2 comma 4, right? Because 2 squared is 4. And you can say another point is 3 comma 9, right? And then so you can put those points in like this bigger set, right? So like that's what we have here. We have 2 different points, negative 2m plus 1 comma negative 4. And negative 6m plus 8 comma 0. So these are 2 separate points, right? Which means that this is going to be one x value corresponding with this y value. This is going to be another x value corresponding with this y value, right? So our set of x's is going to be negative 2m plus 1 and negative 6m plus 8. That's our x's. Like that's our domain, right? And our set of y's is negative 4 comma 0. So like I said, our thing is not, our relation is not a function whenever you have multiple y values corresponding to a single x value, right? And so that's going to be satisfied here if our x values equal each other, right? If they equal each other, that means it corresponds to negative 4 and it corresponds to 0, which means it corresponds to 2 different y values, so it's not a function. And that's the only way you can have it, right? If they are not equal, then you just have separate x values for separate y values, and that's totally fine. So then you have negative 2m plus 1 has to equal negative 6m plus 8. And you just solve this. So that's just 4m equals 7. So m equals 7/4. And then once it has an improper fraction, so that's your answer. Oh, wait. Yep. Yeah, that's your answer. Anything you want to say, Bill?
So yeah, the notation on that problem is it's kind of interesting. So um, if if you have trouble understanding it, it's probably best to just skip the problem because the notation is pretty like it can be hard to understand what the problem is asking for.
Oh, but also, generally you have, if you have like a point of a function, like x comma y, like x1 comma y1, usually you have that in parentheses, not curly brackets. When you have curly brackets, you're usually listing something else on the same thing, right? But when you have like points, you're listing them as with parentheses. So like the curly bracket used there, um, the curly bracket used here is to list points, and the points are listed in parentheses. But so like if we had a domain, we would list them in curly brackets, right? Which I did wrong there. But like if we had the domain of like just positive integers or non-negative integers, I mean, or what? No, positive integers, I'm sorry. If we had a domain of positive integers, technically you would want to list them as curly brackets, as stuff in curly brackets, because um, you're just talking about like one thing you're looking at, which is x, and you're listing them in curly brackets. Yeah. Anything else you want to say?
No, not in this case.
Yeah. Okay. Um, Number 3, a number cube has its face numbered 1 through 6. The second cube has its faces numbered 2 through 12. The cubes are rolled. What is the probability expressed as a common fraction that the sum of the numbers showing is 8? All right. So we have a cube. It's like we have a normal die here, right? A normal die here with 1 through 6 as its faces. And we have a die that its faces are multiplied by 2. And okay, we want to find the probability that the sum of the numbers is 8. Okay, so we first have to realize that all of these numbers are even, right? And if we sum to 8 and we have an even number here, we have to have the even number here, right? So then we only have to consider 2, 4, and 6 here. So if we just consider 2, 4, and 6 here, we see that 2 must be paired with 6, 4 must be paired with 2, and 4 must be paired with 4, and 6 must be paired with 2. Okay, and these are the total, these are the only cases that you have, right? Like if you have a 2 on the first dot, you have to have you have to get a 6. There's no other case that you can do, right? And same thing with all of these, right? And these are just one case on the second dot, right? So that means that each of these are just one case, right? And so that's just 3 cases. That's just 3 possible cases where you can get 8. And if we just find our total number of cases, we can put our possible cases over our total number of cases, and that will give us our probability. And so because all these numbers are distinct, the total number of cases that we're going to have is just 6 times 6, because it's a cube with 6 faces. So that's just going to equal 36. So we can just do 3 over 36. That's just 112. So like maybe you might be wondering, when would these not be just like one case? Well, it could be like if our second die was instead like 2, 2, 4, 6, 6, 12, then these would not be just one cases, right? Because like this one, the 2 here has 2 possibilities, right? And the 6 here has 1 possibility. So for this case, then there would be 2 possibilities for that. And then this one you'd have 1 possibility, this one you have 2 possibilities. Okay, and actually when I did the total number possibility 6 times 6, it actually doesn't matter if they're distinct or not. Okay, anything you want to say, Bill?
No. It's fairly straightforward.
Yeah, this should be pretty straightforward. The perimeter of a square is 16 inches greater than the perimeter of another square. If the area of the smaller square is 48 square inches less than the area of the larger, find the sum in inches of the lengths of the diagonals of both squares. All right, let's say we have a square here. It's a larger square, right? And we have a smaller square here. Let's say the side length is x, the side length is y. Okay, we're given that the perimeter of the larger square is 16 inches greater than the perimeter of the smaller square. What does this mean? Well, the perimeter of the bigger square is 4x, right? And it's 16 inches greater than the perimeter of the second square, which is 4y. And if it's 16 inches greater, then you're adding 16 to the perimeter of the other square, right? And so that's one equation that we have. And it says the area of the smaller square is 48 square inches less than the area of the larger square. So that's another equation. And then we want to find the sum in inches of the lengths of the diagonals. So the length of that and the length of that. So, we should try to solve these 2 equations. We can divide by 4 on this first equation to get x equals y plus 4. And then what we could do is, well, we could plug in x into here, right? And then we try to solve y as a quadratic. Minus 48. And oh, look at that. We have y squared on both sides, so our quadratic component cancels out. So that's very nice. So then we have 0 equals 8y minus 32. And then move the 32 to the other side, then you have 8y equals 32. So then you just have y equals 4. Okay, if you have y equals 4, you can plug it into like this equation and you get x equals 8. And now we want to find the sum of the diagonals. So if this is 8 inches and this is 4 inches, the diagonal of a square is just going to be the side of its square times root 2. You can figure that out with the Pythagorean theorem, right? I think we showed that before, so I'm not going to show that here. But yeah, so the diagonal is just going to be 8 times root 2, 4 times root 2. So then you add that up, and then you get did I do something wrong?
Um, let's see.
Um,
No, it looks right. Let's see, right?
well, it says the answer is 24 root 2 inches.
All diagonals in both squares. So so there's two diagonals for each
Oh,
square.
what?
It's asking for all
That's
diagonals.
find the sum in inches of the lengths of all diagonals of both squares. Oh, that's kind of dumb. So basically, a square has two diagonals, right? So it wants you to sum both of these. So that would be like 2 times 8 root 2, so 16 root 2, and 8 root 2 there. So the actual answer is 24 root 2. I don't know. That's that I think that's kind of
Yeah, that's
bad. I mean, that's just like one word to trip you up.
yeah. So that's yeah. So you just have to watch out for something like that. That's not really normal. So that can really catch you off guard.
Yeah, you just have to be careful with that.
Yes.
Like with this, if you have extra time, you definitely want to read back through the problem and see if you missed like any wording stuff, which I
Even when
miss a
you're
lot.
even when you're like first time reading a problem, you should still be like read it carefully. Be sure you
Well,
completely
well,
understood the
not
question.
too like slow, but
Yeah, but
like
like be sure you
just be
complete
aware of everything.
yeah, be sure
Yeah.
you've completely understood the question before you did the thing.
Anything else you want to say?
Um, I mean, otherwise that problem wasn't all that difficult, so I think yeah, I think I'm fine.
Okay. Also, hold on. I'm gonna get a cough drop.
Okay, so I'll do this problem. Find all integer values of x for which x minus 3 times x plus 1 times x minus 5 is less than 0. So here, what we want to do is we want to just find we want to just find the point at which it equals 0 and then find in which ways you can make it less. So here we can have so we had x
Oh, are you working through the problem?
yes.
Okay.
So it was
I think
x.
um I think 2 hour meetings are kind of long. My throat is getting kind of sore.
Okay. We can see if we can
I,
do
I,
this.
I don't know.
Okay. So x minus 3, x plus 1, and x minus 5. So x minus 3, x plus 1, and x minus 5 is less than 0. So if we have this, we want to find at which point does this whole thing equals 0 first. So and that's x equals 3, -1, and 5. And we want to look for ways in which we can make this lower. So to do that, we want to so we can have x is um so we want this to be negative, right? So we want so the ways we can make this negative is if all three of them are negative, or two of them are positive and one of them is negative. So if all three are negative, if we want all three of them to be negative, x has to be less than what? X has to be less than -1. If we want two of them to be positive and one of them to be negative, um, x would be x x sorry x could be um, what, less than 5 but greater than 3? Yep. X could be less than 5 greater than 3, or X could be, actually, is that it? Or X could be, uh,
Yeah, that's going to be it, right?
okay.
Because if you have one negative and the other's positive, the one negative
Right,
has
the
to be
one
with
negative has to
the
be the lowest
x
one.
minus 5, right?
Yeah,
Because
okay,
yeah, it's minusing the largest.
right. So these are the ways this is negative. All right, and then we're looking for all integer values for of x for which that. So we're looking for the integer values. So if we have this, um, wait, it's asking for all integer values of which of x for which. Right, okay. So it's x is less than -1. We can't really express this as integers, so we can just leave it like that. And also for x here, it can be just, it's just 4. So that's our answer, it will look like? Yes.
Yeah, and all the so in the answer here, all the weird or stuff is just saying like all different ways to like say the solution. So like the or is not actually like in the answer. The each of these four things are separate answers. All right. Um yeah, so like you pretty much just do it like that. Yeah. All right, let's just move on to number 6. The ancient Greeks believed that the rectangle with the most pleasing form was the golden rectangle. The golden rectangle has a ratio of its width and length that is the same as the ratio of its length to its width plus its length. Okay, if the width of a golden rectangle is 1 inch, what is its length in inches? Okay, so I mean, these are just set of equations that we can solve, right? So the length is going to be the longer side. We can call that x, and we can call the width y. So then it says that the golden ratio is a ratio of its width to its length that is the same as the ratio of its length to its width plus its length. So then we have this equation, and then we just have y squared plus, if we cross multiply, we have y squared plus yx equals x squared. And then, oh, whoops, I should not put that equals. Then we have that. And then what? And then we're given that the width y is equal to 1 inch. So then we just plug that in. Then we have 1 plus x equals x squared. So then we have a quadratic equation, x squared minus x minus 1 equals 0. If you try this out, you'll find that it's not factorable. So just use the quadratic equation, and just do it. I hope you guys know the quadratic equation. If you don't, you definitely need to know it. So x equals that. And then you get x equals 1 plus or minus root 5 over 2. Now, root 5 is bigger than 1, right? Because root 1 is 1, and if you have root more inside, it's going to be more than 1. So if you have minus in this case, x is going to be negative because you're minusing something greater than 1 from 1. But x can't be negative because it's a length of a rectangle, right? So that means we had to take the case where it's positive. So then x equals that, and that's our answer. You can see that there.
So
Anything?
something else to know for this problem is if you didn't recognize it, this is the golden ratio. So if you knew that, you could just, you know, get that problem. But yeah, this is just the golden ratio.
Yep, if you knew the golden ratio, you could just you could just multiply it, and yeah. All right. Oops. Um, Three concentric circles have radii of 1, 3, and 6. If a point is randomly selected from the interior of the largest circle, what is the probability expressed as a common fraction that it is in the region bounded by the two smaller circles? All right. Three concentric circles. We have radius of 1, 3, and 6. So this is 1, and then so the radius of this circle is going to be 3, right? So we could just label that as 2 because that 2 plus 1 is 3, and we could just label this as 3. And so concentric circles just means that circles share the same center, right? Okay, so a point is randomly selected from the interior of the largest circle, so basically that, and we want to find the probability that it is in the region bounded by the two smaller circles. So would it just be this interior area? What, Bill?
Sorry, what?
It says what's the probability that it's in the region bounded by the two smaller circles?
Right.
So would it just be like?
Yes.
Does it mean like the annuals, so it doesn't mean like that?
I'm guessing just like, you know, these inner two circles, I guess.
Actually, I think it might be talking about the annulus. It says like the region bounded by the two
Oh,
smaller
right, it's
circles,
bounded.
right?
Okay. So yeah, I think it's just okay. Yeah, I think it's just
Okay, yeah. So you guys have to be careful about that. Yeah. Um, yeah. So it's talking about bounded by the two smaller circles, right? So that means each of the circles has to be the bound of the area that you're looking at. So that means the area that we're looking at is going to be this. And we want to find the probability that it hits this, or like a random point selected is in this, that from the total large circle thing. And so how you can do that is just ratio of areas, right? Like areas basically like, kind of like the probability that something will like land in there, right? So our probability is going to be the shaded area. So shaded area over the total area. Okay, so why don't we just find the total area first? Total area is very easy. It's just the area of the largest circle, and it has a radius of 6. So that means its area is going to be pi times 6 squared, which is just 36 pi. Then what's the shaded area? Well, this is not too bad either, because we can get the shaded area by getting the middle circle area and then minusing it by the smaller circle area, right? So the middle circle area is 4 squared pi. Nope, not 4. What is it? 3 squared pi, so 9 pi. And then the smallest circle is just area of 1 squared times pi, or just pi. So that shaded area, the shaded area is going to equal 8 pi. And this is a probability. You can cancel out the pi's, cancel out a 4 from top and bottom to get 9 and 2. So then our answer is just 2 9ths. And that's our answer. Anything you want to say, Bill?
right. So on this problem, just notice the bounded part.
Yep. Okay, let's move on to 8. Applying 4 distinct lines to intersect the interior of a circle, forming regions within the circle. If M represents the maximum number of regions that can be formed, and N represents the minimum number, find M plus N. Oh, okay. This is kind of a unique problem. I don't think I've seen anything like this before. But I mean, this is just like you can just like I don't even know. You can just like solve it by thinking, I guess. All right. So we have a circle, and four distinct lines intersected. We want to find the maximum number of regions that can be made and the minimum number of regions that can be made. So, okay, wait, Bill, do you think it would accept like a tangent line as
Oh, this it
line?
doesn't intersect the interior. So
Okay,
I don't
okay.
think it would accept it.
Yeah. So, okay, so it probably wouldn't let you have tangent lines because it says that you want to intersect the interior of the circle, so it has to be all the lines have to be secant. All right, so let me just okay, yeah. So I mean the minimum number of regions would just be like if you have like lines like this, right? How do I even explain this? Like to
So
get the minimum number of regions,
you
you don't want the lines to intersect,
yes,
right?
because if you want the line,
If you
if you go,
no, you can.
okay. Because
You
if
can
the
go.
lines intersect, then that would create more regions. So
Yeah, like no, let's say you had two lines, right? And this is three regions. And then if they intersect at a point, well, now you have four regions. Um, how do you say that mathematically? I'm not entirely sure. I mean, you visualize it as like you're like moving the line. Like okay, so like let's say uh I don't even know. Like if you like if we look at this line and we move it like down here so that it crosses like that, well we see that this region remains unaffected because it's like that. And this region was originally this region. This is a little bit hard to visualize, but yeah. So our top regions don't get affected. But our bottom region, it was this, and now it's divided into two. So we just made another region. So you don't want crossing lines. Okay. So this will be our minimum number of regions. We can just count it. That's five regions. And now we want the maximum number of regions. Okay, this one is going to be a little bit harder, I think. All right. So okay, to get the maximum number of regions with two lines, you want them to intersect, right? But then when you add the third line, the question arises: should it intersect at the same point, or should it intersect at a different point? I guess we can just test that out, right? If it intersects at the same point, we're gonna have six regions. Um, if it intersects at a different point, we actually have more regions, right? We have one, two, three, four, five, six, but now we have a new region in the center, which we didn't have before, right? So this is actually seven regions. This is actually better. So basically, we found something out. If you have an intersection, you don't want another line going in the intersection. Why? Because you can do better by not going in the intersection, but slightly out of the intersection. If you go slightly out of the intersection, you will create a new region just by the intersection, right? So so yeah, you don't want to cross it in intersections. You want to yeah you want to intersect with the lines, but not in existing intersections. Yeah, okay. So now the fourth line. Well, well,
so the for the fourth line, you want to intersect with basically the
you want
max.
to
Okay,
yeah,
go.
you want to try to intersect with the most number of lines as possible.
Yes.
And if you can get that without intersecting in existing intersections, that would be the best.
Yes.
Um, okay, and there is actually a way to do that. If we have a line here, it intersects with all three lines right here, right here, and right here, and it doesn't go in existing intersections. So this would have to create the most number of most number of regions, right? So then we can just count. So we're gonna have 1 here, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so we have 11 so far. Oh, okay. Oh, it just wants 4 lines. Yep. So then our maximum number of intersections will just be 11. So then it's just 11 plus 5, which is 16. Okay, that wasn't too bad. I was getting a bit scared if you had to do 5. Can the 5th line intersect all of this stuff?
Theoretically, probably, I think. I think it's possible.
Yeah, it's probably possible. All right. Well, yeah. Hopefully that makes sense. If not, just ask us. Okay. Yeah. So that's all of our target problems. So now I can move on to team. All right. So okay. How many scores are contained in the figure below? Well, let me find some space. Okay. And we have a 5x5 grid, and we want to find how many squares are in there. Okay. So I'm not just going to draw it. Okay. So generally, when you're counting when you're counting shape stuff, you want to like separate it into like different sizes. So we should first count the small squares, the unit squares, and this is very easy. It's just the like the number of unit squares that are in there. That's just the length squared. 5 squared is 25, and then we should go one size up. So the 2x2 squares. How many squares are in here? Well, like we could visualize it. We can see we have a square here, right? And we have another square here, and we have another square here, and we have another square here. So in this first 2-row thing, we're gonna have 4 2x2 squares. And then if we move down to here, we're also going to have 4 2x2 squares. If we move down to here, we're also going to have 4, and if we move down to here, we're also going to have 4. So that's just all of these plus each other, and that's 16. And none of those squares overlap, so yeah. Now we should count 3x3. So again, we can use that thing. So we can see a 3 by squares here, and then we can move it 1 over. So that's another one, and we can move it 1 over one last time. So that's going to be 3 in our first 3 rows. And we can move all of that down 1 row, so that's going to be 3 more, and that's going to be 3 more. And also, you might see that there's actually a cool pattern here, and it's that this is 5 squared, this is 4 squared, and this is 3 squared, right? So that's kind of cool, and it does work, yeah. So this 4 by 4 should be 4, and if we look on the thing, it is, right? Because we can have 1 here, we can have 1 here, we can have 1 here, one here, and we can have 1 here. So that is 4, and then when we look at 5 by 5, I'm not going to draw it, but it's just going to be 1, right? Because that's our entire square. Okay, and then you just add them up. So this is 10, this is 20, so that's 30, and then 30 plus 25 is 55. Anything you want to say, Bill?
No, a problem like that it's really straightforward. There's not really any point. So yeah,
Yeah.
it's just fairly simple.
A bank issues credit cards consisting of 9 digits to prevent people from giving fraudulent numbers over their phone. The card number is designed so that its 9th last digit is the integer remainder obtained when the sum of the 2-digit numbers formed by the 4 pairs of preceding digits is divided by a 1-digit integer x. If that is are valid numbers. What is x? Okay. Let's try to dissect this a little bit. So we have a credit card. We have credit card numbers, and they have 9 digits. And so we by reading the problem, we see that it's kind of separated into the ninth, the last digit, and 4 pairs of numbers like that. And then it says that the last number is the integer remainder obtained when the sum of the 2-digit numbers. So we're going to have 2-digit number here, formed by the 4 pairs of preceding digits. So the sum of that is divided by some integer, 1-digit integer x, and the remainder of that is the last digit. Okay, so if we have this 2-digit number is A, and this is B, C, D, and our last digit is E, it's saying that if we sum A, B, C, D, and we divide it by, and then we modulus by x, then we get E. All right. And then it gives us 2 examples, and it wants us to find what x is. So let's go ahead and apply it. So we want to sum up all of these numbers. So 97 and 83, well, that's just going to be 180. And then 46 and 38 is just going to be 84 plus 5 is 89. So that's just going to be 269. Okay, and then it's going to be modulus by some integer, and it equals 5. So let's just leave this as one equation for now, and let's find the second equation, and then we can find what x is. 79 plus 86 plus 95 plus. Actually, I'm just going to do this on the calculator because I think all of you guys can add numbers. If I can find my calculator. Okay, so that is going to equal 326. And so 326 modulus x is going to be 2. Now how do you think we should solve this, Bill?
So if it's modulus x equals 2, we can subtract 2 from 326, find the factors of it, and do the same for the other one, and do the same for 256, and find the factors and find the common factor.
That's a good way to do it, right?
Find a one-digit
So it's
common
like
factor.
if you have a modulus equation, like a modulus x equals b, you can like between these two numbers, you can like subtract and add, right? Like if we had I don't know, 5 modulus 2 equals 1, you can subtract 1 from 5 and 1 to get 4 modulus 2 equals 0, and this still satisfies this thing, right? So we can do the same thing to this. We can minus 2 on both sides, so that 324 modulus x is 0. And what does this mean? Well, if you have something modulus something equals 0, then the something that is doing the modulus has to be a factor of the something that is being modulus. Okay, yeah. So in this case, x has to be a factor of 324. So then we can just prime factorize 324, and we know x has to be a 1-digit integer, right? So we can just prime factorize it, and also include digits that are not primes. But like we don't have to look at all the factors of 324 because x has to be a digit. So okay, let's go ahead and prime factorize it. So it's going to be 62, and then 81, and then that's just 99. So it's going to be 2 squared on 3 to the 4. Okay, and we'll just leave it like that, and we should also do it to this. So we can subtract 5 on both sides. this saying x is a factor of 264. So then we can prime factorize this to get okay, 311 here. Okay, so then we should find the factors that work here, right? So what digits would be factors of both of these numbers? Well, there's 1, there's 2, there's 3. There's 4 because this has 2 squared. This also has 2 squared. There is not a 5. There's 6. Both sides of 2 and 3. And there is no 8 because this side only has 2 squared. And there is no 9 because this side only has 1, 3. So we only have to look at these digits now. So so we should look at our original modulus equation. So it's kind of weird. So like I said, you could like subtract and add numbers on both sides, but this original thing might not be fully simplified, right? So but it's telling us that it is fully simplified because it is the remainder, right? If you have the remainder, then it is fully simplified. And yeah, so okay, so like what I'm saying is that if x equals 1, it does not work, right? Because if you have 326 modulus 1, this so okay, so the fully simplification of this is 0, right? Because 1 goes into 326 and 326 is a multiple of 1, right? But this technically is still correct. Like the equation is correct because 2 modulus of 1 is equal to 0 as well. So like I don't know, you have to be careful about that. So we can eliminate choices by looking at our original equations and seeing which ones are not fully simplified. So it can't be 1, right? Because fully simplified, it should not equal 2, it should equal 0. And then it's not going to equal 2 either, because fully simplified, it would equal 0 as well. 3 is fine here. It's not going to be here, right? Because essentially, you can eliminate all the numbers that are lower than 5. Why? Because modulus season.
Hey Austin,
Oh yeah, what?
you made a mistake when you were adding. You weren't supposed to add the last number. You only add the first 4 numbers. You don't add the last number.
What do you mean?
When you're adding, you added the last number, so you added the 5 numbers.
Oh, 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 okay, yeah. Wait, how did you notice that?
What?
How did you notice that?
I I noticed 7 wasn't a factor and 7 was the answer, so I was like, you probably added that. So I
Oh
checked.
man. Oh, okay, yeah. So we accidentally added the last number here, and we're not supposed to. So we did everything wrong. Weird. All right. Okay. So we had 269 here, but we actually don't want the 5. So it's going to be 264 instead. Modulus x equals 5. And then we accidentally added 2 to this one, so we have to minus 2 from it. And in modulus x is 2. Yeah, sorry for that mistake. Now we have to redo everything essentially. So again, we want to make it modulus equal to 0. So then we have 259 modulus x equals 1. Oh no, 0. And then 322 modulus x equals 0. We want to prime factorize it again. So we see 2 doesn't work, 3 doesn't work, 5 doesn't work. So we should test 7. If we test 7, then we get it does work. We get 37, and 37 is prime. 322. We continue 161, and then we see 2, 3, and 5 doesn't work. So we should test 7, and we see that it does work, and it equals 23, which is prime. Now, x has to be a factor of both these numbers, right? And the actual only one-digit factor that both these have is 7. So then x has equals 7. Oh, okay. Actually, 1 does work. One are factors to both of these, but again, like I said, if you plug in 1 to here, it's not fully simplified, but it has to be fully simplified from saying that it's the remainder. So x has equals 7. All right. Anything you want to say, Bill?
Um, right, no. Just be wary of doing like what Austin did and adding the last digit by adding the last number by accident. So when you have like a long question like that, make sure you've understood the question before you actually start solving it.
Yeah, my mistake. All right. Let's move on. Kind of running out of space, but oh well. So 2 six-sided dice have their faces labeled with the digits of those. Um, Wait, 10 isn't a digit. Wait, what?
um,
Is that just their mistake?
I guess just yeah, it's probably just
Okay,
label code.
sure. If the dice are rolled, what is the probability that the 2 faces showing have numbers that could correspond to any 2 sides of a right triangle, given that all 3 sides of the triangle have integral lengths? Express your answer as a common fraction. Okay, so it's saying like, so we're gonna roll 2 dice, okay, and then we're gonna get 2 numbers, x and y, and they're going to be corresponding to any 2 sides of the right triangle. So it could be the 2 sides. It could be the 2 legs, but it could also be a leg and a hypotenuse. And it's saying that the um the other side has to be an integer as well. And then we're looking at the probability that we can get that we get x and y from or like that we get an x and y that satisfies these conditions from the dice that have those numbers. So kind of a I don't know, kind of a long problem. But so obviously what we do here is we look at Pythagorean triples, right? Because Pythagorean triples are are the are the like integer sides of right triangles that fit the Pythagorean theorem conditions, right? So if we look at like the smallest Pythagorean triples, we have 3, 4, 5. We can multiply this by 10 to get not 10. We can multiply this by 2 to get 6, 8, and 10. And we can multiply by 3 to get 9, 12, and 15. But we can see that we're not going to get this from our dice, right? Because none of these numbers are even listed on there. Okay. What else do we have? 5, 12, 13. Well, it's not going to work because we don't have 12 or 13. We have to have at least 2 of them, right? Is there any other
I think that's it.
yeah, the other Pythagorean triples are too large. So really this is all that we can do. Oh my, what is that?
Um, yeah, that's everything.
So our 2 possible right triangles can only be this, right?
Yes.
And so what this means is is our possible pairs of numbers are 3, 4, 3, 5, um 4, 5, 6, 8, 8, 10, oops, and 610, right? Like you just have to get two numbers that fit a Pythagorean triple, and then then the other side has to be an integer side length, so then it like satisfies everything, right? So how many cases are these, right? We have no duplicate stuff. So each of these cases is a distinct case, and they're just going to have one possibility, right? So that means we have 6 possibilities in here, and we have 2 dice. So the total number of possibilities is going to be 6 times 6, or 36. So then we did something wrong. We got 1/6 here, but the actual answer is 1/3. So we missed 6 cases. Oh, okay. I'm done. So what we missed was that you can flip each
Yeah,
of
I was
these
about to
cases,
say
right?
you can flip them.
So like it's like for 3, 4, you can get 3 on the first die and 4 on the second die, but you can also get 4 on the first die, 3 on the second die, right? And all of these are flippable, right? Because they're all two different numbers, not like the same number. So that means our total number of cases is going to be 6 times 2 because all of them are flippable. So then we have 12 over 36 again, and that's 1/3. So that's your answer. Anything you want to say, Bill?
Um, right. No, this is still
Okay.
fairly simple.
Oh. Um. Oh, okay. Interesting. Find the perimeter of the polygon below. Oh, what the heck? Is that an infinite polygon? Oh no, it's just very weird.
Austin was
Oh
scared
my
there.
goodness, why? Why is it like this? Oh my god. Okay, what are you gonna do? Okay, I'm trying to make it as big as possible so we can
Wait, is it
try to see
infinite?
it. Wait, what?
Is it infinite or not?
No, it's not
I
infinite.
can't really
It,
see it honestly.
yeah, I know because it's so small. It's not infinite. I mean, if it were infinite, that would be I don't know. That would be crazy.
Infinite is probably too hard, so it's probably not infinite.
No, but yeah, if you look at it closely, it's not infinite. But
Okay.
it's just so oh my
So
goodness.
clustered. Yeah.
Yeah. I don't know. Okay. Okay, I'm gonna make it the entire screen so we can just look at it for a second. Okay. Okay, so we have this, and you can see that it's not
Oh
infinite
man, that is
from the thing
tiny.
ending. It is so tiny. Yep. How do you even see that on the actual paper?
I don't know,
Well,
man.
I guess this was 1990. They're still figuring things out.
Yeah.
Maybe. Okay. Let me try to draw the thing here. Actually, could you
What?
could you take a screenshot of this and then send it to me?
Oh yeah, that's fine.
All right, to be good.
Yep.
All right. Okay. Cool. So now let me draw it here. Okay. And I'm gonna draw not scaled so that we can actually see everything, right? So we're gonna have a thing here. This is going to be 32 root 3. And then this is a triangle like this. And this is a right angle. And this is a very large triangle. And this is 32. Okay? And then we have this is 16. So okay, this is a right angle. This side length is 16. And then we have another right angle triangle thing here. And these lines are not the same line. It's I didn't draw it perfectly, but this line should be like slightly slanted up. All right, so this is 8. And then there's another right triangle right here. And this side length is 4. And then there's another right triangle. And this side length is 2. And there's another right triangle. And it finally merges back with the original thing, actually. And then that's a right angle right there. And this is 1. What kind of problem is this? All right. And we want to find the perimeter of it. So we've got to find this side, this side, this side, this side, that side, and that side, and that side. All right, let's just find this side first because it's easy. So we just apply the Pythagorean theorem, right? So then that's going to be 3 times 32 squared, and that's going to be plus 32 squared, and the square root of that is going to be this side. And that's just 4 times 32 squared, which is just 2 squared times 32 squared, right? So that's just going to equal 2 times 32. So this is 64. And Pythagorean theorem here, right? So 32 squared equals 16 squared. We can just call that x plus x squared. I mean, 32 is 16 times 2, right? So that's 4 times 16 squared equals 16 squared plus x squared. So then we have 3 times 16 squared equals x squared, or x equals 16 times root 3. So this is 16 times root 3 right here. And then we have 16 and 8. Oh, okay, but so here's the thing, though. Here's the thing that makes it easy. All of these triangles are similar, right? They're all right triangles, and the ratio of the hypotenuse to the leg is 2/1. So, and this is 2/1 as well. So that means that the ratio of this to this and this to this have to be the same, right? And this is just times root 3, so this has to be root 3. And we can apply the same thing to all of them. So that's 4 root 3, that's 2 root 3, and that's 1 times root 3, or just root 3. Now we add all of them together. Actually, this is plus 63. Did I miss something? Wait, why is it plus 63?
Because what the top side is 64 minus 1.
Oh, this top side, okay, right. So this triangle merges with the original triangle thing, right? And this 64 side was the entire side, right? But this 1, it takes out 1 from the 64 side. So the perimeter of it is actually 63. And then you add up all the root 3's on the outside. So then that's 32 plus 16 plus 8 plus 4 plus 2 times plus 2 plus 1. And those are all powers of 2, right? So that means it's just going to equal the next power of 2 minus 1. I mean, if you don't know that, you can just add them up as well. So so it's going to be 64 minus 1, 63 times root 3. And then you add this to 63, and that's your answer. What kind of problem was that?
It's very weird. Especially the graph. The graph was very hard to see.
Yeah, that was pretty weird. I guess it's 1990. Do you think we should skip to like later years? I don't know.
Maybe. I think we should maybe start in like 2000s. These problems, they run the risk of being not relevant anymore for today's because they might have taken some like
Yeah,
questions
and
out.
we do have the risk of missing relevant questions, right?
Yes.
Um, yeah. Okay, so let's move on to number 5. So in a computer game, Adam allows 5 points for each game he wins, 7 points for each game his younger brother wins, and 3 points for each game the computer wins. After a certain number of games, all three have identical scores. What is the fewest number of games they could have played in order for this to be possible? For this tie to be possible. All right, so Adam gets 5 points for every game he wins. His younger brother gets 7 points for each game he wins, and the computer gets 3 points for every game it wins. And at some point, they all tie, and it wants to find the fewest number of games they could have played for this tie to be possible. Well, we just need to find the GCF of these numbers, right? To find the tie, the lowest tie that they can get. And because they are all prime, the GCF is just going to be all of them. Oh, not GCF, sorry, LCM. Because they're all prime, the LCM is just going to be all of them multiplied together, which is just 15 times 7, which is 105. So for them to tie, this is the lowest number that they can tie at. And then it wants to find the number of games that they have played to get this tie. Well, Adam, he's going to play 105 over 5, right? And his brother is going to play 105 over 7, and the computer is going to play 105 over 3. But remember, 105 was just 5 times 3 times 7, right? So we can just cancel these out, and these numbers are just going to be the other two numbers multiplied together, right? And then now I just add these. So 21 plus 15 plus 35, that's just 71, and that's your answer. Anything you want to say, Bill?
Yeah, that wasn't too complicated. I think that's really simple. So, yeah, I think that doesn't really need an explanation.
Oh my, what is this?
Oh
It's
my
a balance
goodness.
problem.
Oh, it's a balance problem. Oh no.
Okay.
Okay.
We should probably move to later years.
Yeah, balance problems aren't really relevant anymore.
And we
They,
we are like we're not in the pace to finish all of these years, right?
yes.
Like
Yeah, we're not
we
really.
we, we've done a lot of meetings, and we're still in 1990.
Yes. So we
Um,
should probably go to later
we
years.
should probably skip to maybe I don't know.
Somewhere in the
What do you think?
2010s probably.
2010.
Like start with 2010.
Maybe we should just start with like well, okay, we I don't know. Okay, we can discuss this later.
Okay, yeah.
Let's just do the scale problem
Yep.
right now. If each of these figures represent objects on a balanced scale, express the shaded oval in terms of the circle. Okay, so okay, let me call circle equals x, square equals y, triangle equals z, and oval equals a. Okay, and now if the balance is balanced, that means I mean it doesn't really make sense, right? Because like it's like the weight of the object. Um, I don't know. Okay, but okay, yeah, sure. Let's just say this is the weight of the objects. Okay, and for a balance to be balanced, the weights of these two objects have to be equal, right? Well, I mean technically not because like if you have like if you have, I mean this is like physics, right?
All right,
Like if
let's
you have
not discuss the physics of this problem.
if you have objects closer to the
All right,
fulcrum,
let's not
then
do
it's going
this.
to have a smaller torque than if
Let's
you put
not.
it on the outside, right? Okay, but whatever.
Yeah, let's not do this.
Let's just say that
Yeah,
they are all concentrated at one point.
yeah,
All of their weight is concentrated at one point, and it's the same distance from the other point as the other. Okay, whatever.
yes.
Okay, whatever. Okay, so from the first thing we get that what 2y plus z equals 8x. Then y equals z plus x, and then x plus a equals what? We only have three equations here, so sure, whatever.
Right, because we're
Okay.
representing it in terms of
Yeah. Okay, so we can substitute y here and here and here. So we get 2z plus 2x plus z equals 8x, and that's what 3z equals 3z equals 6x and z equals 2x. Okay, and then in the bottom one we have x plus a equals z plus x, or a equals z. Well, if a equals z, you can substitute a in here, right? So a equals 2x. We want to find the ratio of a over x, right? Expressed in terms of oval, in terms of circle. So then it's just oh, well, it doesn't want the ratio, it wants an expression. So
yeah,
okay, sure.
that is what
Okay,
it
let's
wants.
just get a over x is 2, right? From this a equals 2x, we can divide by x on both sides. A over x equals 2. Okay, and then what this means is that we're going to have double as much of, no, what?
What are you trying to achieve here?
No, okay. So this means that we have double. What?
You're expressing the list in terms of the circle. You're saying
Oh,
that.
okay. You're expressing the weights, not like. Oh my gosh, I don't like
What were
this.
you trying to do there?
Okay, never mind. Okay, so it's saying like you have you're expressing the oval in terms of the circle, like their weights. Like yeah, because we're working with weights down here. So we have the weight of the oval equals 2 times the weight of the circle. So then to express that in drawing, you write oval equals 2 circles. And that's your answer.
That is your answer.
All right. Yep. So okay, that's going to be all for today. Hope you learned something from our meeting, and that's it.